freezing. Things you can move, and that would be lone pairs or multiple bonds. And multiple bonds, I mean either double or triple. So you cannot move a single bond like right here, because that would actually move the connect. Like if you move this bond over, let's say to nitrogen, that would break the bond between carbon and nitrogen, and they would no longer be bonded together. Okay, so for resonance, you have to keep the basic backbone the same. So since this starts off CH3 bonded to nitrogen, bonded to carbon, bonded to oxygen, this still has to be CH3 bonded to nitrogen, carbon, oxygen. Now how many bonds are between each one will change, but the actual backbone right here will not change. Okay, so what I see here is on the original structure, we have a lone pair, we have a multiple bond, and a lone pair. Okay, anytime you see lone pairs and multiple bonds close to each other, that's where your resonance will be. Okay, so there will be no resonance over here because this is just a single bond. Okay, now the other thing is okay, so electrons are negatively charged, okay? So they're going to be attracted to two things. First, they're attracted to, okay, sorry, this just went away again. Okay, so they're going to go towards two things. First, electrons, oh my goodness. Let's go back. Let's not do that. Okay, let's see if this works this time. We're going to get this eventually. Okay, so the lone pairs will move towards two things. One would be just a positive charge. Okay, because think negative is attracted to positive. The other thing would be an electronegative atom. Electronegative atom. Now, the reason an electronegative atom, because by definition, an electronegative atom is a lover of electrons, okay? So they're so attracted to electrons, they're going to pull them towards them. So if we look in this structure, we don't have a positive charge in here, but we do have a very electronegative charge, which would be oxygen right here, okay? So they're going to go towards the electronegative atom. Now, if there was both in there, say electronegative atom and a positive charge, it's going to go towards the positive charge because the positive charge is an actual charge, okay? But there's not, so it's going to go through to the electronegative atom. So you go to the end of the, or I guess what you could do here. So here's a double bond, here's a multiple bond you can move. Oxygen is the most electronegative atom on the periodic table, so this double bond is going to want to move to the oxygen, okay? So when we do that, we'll have a single bond between oxygen and carbon. Okay, now remember that a bond is made up of two electrons, so that basically moves a lone pair over. So we had two lone pairs there already, okay, and then we just moved one more over. Okay, so when this bond moved to oxygen, it made this extra lone pair right there. Okay, now see, and then there's a double bond that's right here. Okay, well now carbon only has 3 bonds. That's not happy. So it wants more bonds. So if you move one bond, you're going to have to typically move another one to stabilize. So we're going to move this lone pair right here. Okay, so it'll become a bond. So now there's a triple bond right here and no lone pair on nitrogen because we moved it to become a bond. Okay, so let's check everything, make sure it's not violating the octet. Carbon has oxygen, 1, 2, 3, 4, 5, 6, 7, 8. And carbon 1, 2, 3, 4, 5, 6, 7, 8. And nitrogen 1, 2, 3, 4, 5, 6, 7, 8. I don't have to check this CH3 right here because I didn't do anything with it. So everything has an octet, so that's good. Now, let's look at their formal charge. Nitrogen on the periodic table should have a valence of 5, but let's see what's in the structure. I see 1, 2, 3, 4. Okay, so we're just looking at contributing electrons, the ones that are basically just touching nitrogen. Not shared, but just the ones contributed by nitrogen. So 5 minus 4, nitrogen has a +1 charge. +1. Okay, carbon should have, so it's nitrogen. Carbon, let me do it down here. Carbon should have 4 on the periodic table, and it's contributing 1, 2, 3, 4. So that's good. So 4 minus 4 is 0. No formal charge. You prefer not to have any. And then oxygen should have 6 on the periodic table, has 6 valence electrons, and it's using 1, 2, 3, 4, 5, 6, 7. So it gives it a -1 formal charge. So you see, still overall it's 0. You do +1, -1. Okay, but there's a formal charge and on nitrogen and oxygen, so those aren't completely stable. Okay, so that's the resonance structure. Now in the problem, it wants you to do the arrows going forwards and back. So let me change this to green. So this is how you move the electrons. These arrows are they're just showing the movement of electrons, okay, to the most stable resonance structure. Okay, so now it wants you to show how do you go back. Okay, I showed you how to go to this. How do I go back to the original structure there? Well, you just reverse the arrows. So instead of the arrow pointing to oxygen, I'm going to go from oxygen and make a bond to carbon. Let's put that bond back. Now right here, I move this extra bond, and it was on nitrogen as a lone pair, so now I'm going to put that as a lone pair on nitrogen. And then if you redraw it, you will get this original structure right here. So try a few and let me know if you're still having trouble.